In this video, we're going to be looking at the law of conservation of mass. The law of conservation of mass is defined that within an isolated system, mass cannot be created nor destroyed. The term isolated system may sound a bit tricky, but all it does is that it refers to an enclosed area or space where energy or mass doesn't freely go in or out, kind of sectioned off from the rest of the environment. In actuality, an isolated system is very hard to achieve, and it's actually pretty much impossible. It's largely theoretical, but we assume that all these chemical reactions are occurring in an isolated system. So that's why the definition is stated like that. Awesome. Now let's look at the law of conservation of mass energy, which has a lot of misconceptions within chemistry and may get a bit confusing. And what this states is that in an isolated system, mass or energy cannot be created nor destroyed. Now, on a chemical scale, it is usually insignificant. The amount of mass that's converted into energy is usually insignificant, so we just focus on the mass part of the equation here. We just focus on the law of conservation of mass. So if you're looking at your average titration or your combustion or your single displacement, the amount of mass that's actually converted into energy is very, very minimal. So we don't even consider it. However, when we're looking at nuclear chemistry, that's when huge amounts of energy are produced, and that's when you need to look at the conservation of mass energy. So it's important to make that distinction. In normal chemistry, typically you don't need to consider the energy aspect to it because the amount of mass that's converted into energy is very little. But on a nuclear level, it is very important to consider both mass and energy. Awesome. Now in chemistry, the law of conservation of mass is typically associated with chemical reactions. And I drew out a chemical reaction right here, where you see carbon dioxide and water turning into glucose and oxygen. And this is the process of photosynthesis. Flashbacks to biology class. And in this reaction, and if you were to follow the law of conservation of mass, mass cannot be created nor destroyed within this reaction. So that means the mass of the products, whatever you put on this side, is going to equal the mass of the reactants, whatever you put on this side, is going to equal the mass of the products. So when we look at these chemical reactions, these are all in forms of compounds and atoms. So if we were to break that down a little bit, that essentially suggests that there has to be the same number of atoms of each type of element present on both sides. So what that means is that there has to be an equal amount of oxygen atoms on both sides, an equal amount of carbon, an equal amount of hydrogen atoms on both sides, because that essentially will ensure that the mass of the reactants will be equal to the mass of the products. So it works both ways there. All right, and this is why you need to look at coefficients and balanced equations. So let's balance this equation very quickly. On this side here, we see 6 carbon atoms, and according to the law of conservation of mass, we need the same amount of carbon atoms on this side of the equation. So I'm going to draw a 6 coefficient here. And this side over here, we see 12 hydrogen atoms, and according to the law of conservation, we need 12 on both sides. 6. And then now, on this side, we have 6 times 2, 12, plus 6 times 1, 6, so 18 oxygen atoms. You have 6 more here, and you need 12 more. So you're going to draw a 6 here. All right, so now this equation is balanced. And what I was trying to show there is that the law of conservation of mass is essentially the whole reason why we balance reactions in chemistry. It's the reason why we see these coefficient numbers. All right, now let's do a quick practice problem. If I were to have maybe 3x of carbon dioxide and maybe 2x of water, and say that produces about 4x of glucose, and x isn't a given number, let's just use that as a common variable here. How much oxygen will we have? All right, now obviously for this question we're going to use the conservation of mass, and as we see over here, the mass of the reactants has to be equal to the mass of products, right? So we're going to have 3x plus 2x. So on the reactant side, we're going to have a total of 5x of mass. And on the product side, we already have 4x. And we need it to be equal to 5x because the mass of the reactants is going to be equal to the mass of the products. So the answer here is going to be 1x, because 4x plus 1x is going to equal 5x. So therefore, you're going to have x of O2. All right, so hopefully that made sense. In this video, we looked at the conservation of mass and how it's applied. If you want to look forward to future videos, please consider subscribing to the channel. Please like this video, and I'd like to see you guys in the future. Thank you.